This discussion tonight's going to be a little bit dry. We've got a few highlights, but want to cover some fairly low-level stuff at this point. A lot of that is just so you guys can get used to what we're trying to train for when we're doing generative modeling, or even use deep learning in general, essentially. Okay, yeah, we can probably get started. So this time we're looking at exploring the latent space in deep learning. And we'll get into what the latent space means and how that all sort of affects how we train and how we use deep learning models and how we can use them to do generative modeling. Okay. So what we'll do first, though, is cover the $100 code bounty. And that was, the contest was the best face from the Gen 2, which is from the Chapter 2 DC GAN example that we looked at last time, just before Christmas break. And we have one entry from Dave B. I think you trained that, you said, Dave, at about 60 some epochs or so, was it?
Yeah, about 60. I did do it a few times because Colab was cutting me out. I let it run. Of course, I wasn't around for half an hour, so it shut down to restart. So, and then I actually had to do it in pieces, and I hit my limit on GPU. So,
oh, really? Okay.
Yeah.
Okay.
And I was able to determine how to save the model so that I didn't have to start at zero again. I could reload it and then start training again. But yeah, that's as far as I could get. It was about 60. Yeah, it was closer to 70, and then the whole thing just shut down because I hit my limit.
Okay. Yeah, so actually here, I didn't really discuss much of that. So let me just go through here. I'm just gonna set up a new share with this example. So just let me know if you can or can't see my screen there. Okay, so what we should be looking at is the Gen 2 DC GAN example on Colab. Can we all see that? Dave, can you see that?
You still have my image slide up? Unless maybe I've got a different
window. Okay, there. Yeah, I'm not sure why the sharing is different for this version of Zoom I'm running than it is for the one I use at work, is I can screen share a whole screen and then just switch between apps instead of having to share just the app itself. Okay, can you see that okay now?
Yeah.
Okay. So this is the example that we're sort of working with. This is some of the DC GAN will essentially be the basis for a lot of the GANs we're going to look at up until fairly advanced models. It is sort of a really established good pattern that you can use for all GAN examples. The GAN that we looked at was using convolution. So this is essentially DC stands for a double or dual convolutional GAN, meaning that it's using convolution basically as in the discriminator and the generator. So if we remember, we downloaded the images from my Dropbox folder, and that was the Celeb A data set, which is essentially a bunch of faces. And then we applied the transforms on that to essentially we're just adjusting the image size. So we're center cropping in about 70% of the image so we can get a zoomed in view of the face. And doing that just allows us to easier training, easier generation and stuff like that than rather having a bunch of noise around the subject's face. And then this is how just sort of basically loading up the data sets. I've already covered most of this in other previous, but I'm just going to cover this quickly again. This is going through an iterator, which is just a quick way of, or a functional way of loading images while you're training instead of filling up your whole memory. The data set allow you to sort of do batch loading of these images. And then what you can see here is just essentially one batch of images. And then this is our generator. So the generator here again is using convolutional blocks to do that feature extraction from the images, right? And we can see that when we look at the example of, you can see little pixelation pieces where it looks like it's placing the wrong features in some areas or it's getting the right features in some areas. That's a result of convolution and the level at which we're extracting features. So, and that has a lot to do with the settings we're using for the convolution and stuff like that. But we're not going to get into that so much this time. Here's the discriminator block. Discriminator. It's using this thing called a block, but essentially the same thing. It's just convolutional layers stacked on top of each other. And then these are the optimizers and how we're creating the model. Sorry, the optimizers are down here. So we're using an atom for this one. And here's our basic sort of training loop. So we go through the number of epochs and then we iterate through our training loader. So the loader that's loading the images for us. And then we calculate our loss. I've gone through this already, but we'll go over it again. Essentially, as we're going through, we're plotting the history of the discriminator loss, the generated loss, and then also for the discriminator, we're doing the fake versus real loss. And then here's our charts. And here's my example. I did it for about 99 epochs. For me, I'm running Pro, so I'm not sure if it's a reason, but I've ran Collab without Pro, and I've not had very many issues like you described, but one thing to keep in mind is being aware of the runtime stuff. So if the runtime gets interrupted for execution, it generally means if the runtime isn't totally destroyed, you can actually just restart the training of the model. It'll start at epoch number 1, but the weights in the model will be the same. So if this was stopped for some reason, I could actually just go up here and run this again. If you are constantly creating new models on the same runtime, that's where you can run out of CUDA memory or GPU memory, essentially. So in order to avoid those times, if you feel like if you need to rebuild models, you'll generally either want to do a restart and run all. And restarting is a little different than a factory reset. A restart just means that you're sort of just restarting the server, and essentially any files that are stored on the drive will still be accessible, as opposed to a factory reset, which will actually reset everything. So the difference is if you have an interrupted execution, you can sometimes rerun models. If you want to reblow away everything and regenerate everything, you'll do a restart and run all. But if you're getting some weird CUDA issues or GPU issues, then you'll generally want to do a factory reset runtime. Okay? So I just wanted to cover that because you mentioned those problems and we haven't really discussed those that much. Okay, so let's go back to the presentation. Okay, so Dave, you're the only submission, so we'll count you as a winner. The idea here was that we'd vote on this. You can see here, there's some pretty good faces here and here. Overall, I would say, but you can see some of the features are getting overlaid. You can see the pixelation in some of the features, and that's a result of the convolution and stuff like that. And some of it's going to be about the learning rate and some other factors we'll look at as we get into this session. Okay. So what I'll talk to is about our progress. So right now we're sort of looking at about chapter 3 in the book that I had written, which is Generating Reality is the book. It's for a press. I'll probably be giving away maybe some free copies in the meetup as well later on. But this is where we are right now. It's probably about chapter 3 is what I'm sort of referring to. And you can see this is where we're going to go to is much farther down into a lot of different things. So we're just really starting to cover the surface essentially. Okay. So if you feel like you're falling behind or things are not making a lot of sense, if you email me at that email address, I most likely may have another special class in February for an intro to deep learning with PyTorch. give a lot of opportunity for people to sort of follow up, learn about the basics of deep learning, and then catch up and join the class, especially if you feel like some of this stuff is getting over your head or you're not sure how I sort of picked up some of those examples. And that DC GAN one is an example of one of a model that will be evolving a lot through the various course of the events of the meetup. So don't be too hung up if you don't understand every little neat detail about it, because we'll be reviewing a lot of that as we go through, and we'll be going through plenty of examples for how to use that and how to sort of modify that example to various other implementations of generators and stuff like that. Okay, so what this whole session really is about is what are deep learning models learning? Okay, anybody want to shout out what they think deep learning models are learning? Anybody feeling somebody must know? No? Nobody wants to be brave and shout out? Okay. Okay. So really what we're doing in deep learning is we're doing function approximation. And you can think of that, and we'll get into an example so we can look at that in a little more detail. But really all deep learning does is it just function approximates, okay? And it's just approximating a function that can either fit a set of data or fit a function itself or fit some distribution of data, which we'll get into. And this is used throughout deep learning for things from simple classification models all the way up to deep reinforcement learning. So reinforcement learning itself is a set of equations for how an agent might explore an environment. The way we make it deep by adding deep learning to it is we actually just use deep learning to approximate that reinforcement learning function. So that's a really extreme case of using deep learning to provide a sort of engine for reinforcement learning. So that's really what deep reinforcement learning is we're just using deep learning to approximate the reinforcement learning function. But we'll use, deep learning for a lot of different function approximations, as like I said, from classification examples to just, doing basic functions. So let's look at an example here of a coding exercise. And I'll share my screen again. So this example is up on the GitHub repo, and this is called Gen3 function approximation. Okay, and this is a really simple example, really simple network we'll look at. And what we're looking at here is we're just going to develop a deep learning network that can approximate this simple function, x squared plus 5. Okay, really, really quite simple. So what we're going to do is we're going to generate a NumPy array of data of 1 to 10, and then we're going to fit that into a function. So the function here is this that takes the x, and that's going to give us our y's. Okay, and then the inputs, I'm just taking the shape of the first parameter, which gives me the inputs. So I know the number of inputs are 1. Keep in mind, this is a one-dimensional problem, right? So this is a very simple one-dimensional problem. If you think of our MNITS classification with fashion or handwritten digits, that's a 784 dimensional problem because it's 28 by 28 pixel image that we're trying to classify, right? So this is a very simple problem compared to what we're going to be looking at much later. Just keep that in mind. So this inputs just tells us how many inputs are in the model. In this case, 1. You can see it's showing 1. This reshape is just a reshaping of the data, and that's just for the learning because we're going to do matrix multiplications. So that's what that's about. And then this plot is just plotting the x and y so we can see what that actually looks like on a graph, right? So we can see what the function looks like. So what we're going to do here is going to just do a basic train test split, and we're using the test size of 20% and no randomness. Okay, and that gives us a new number to train of how many samples, which will be 8 in this case. And you can see there's the 8. And then we set our X train to that and our Y train to that. And then this is our model here. And this model is maybe, it could be oversized, but so we're using the inputs 1 into a 50 neuron network. So quite a wide network essentially for this this complexity of problem, and then 2 other layers of the same size, and then finally we go back down to 1 as our output, right? And that 1 output, we're using the loss function of mean squared error loss to determine what our loss is. And mean squared error loss is essentially just taking the difference between our predicted number and our real value and squaring and taking the error, okay? And that's what our loss function is using to push the error back through the network. And then you can see through my optimizer here, what I'm setting is the learning rate is a hard-coded value of 0.026. And this is going to be important. We're going to look at this learning rate and what effect it has on the network. And you can see for this network, I'm training this at 8,000 epochs, which for this type of problem is quite a bit, but just to also show a point. Okay, and the rest of these here are just reshaping and of the data. This again is just some reshaping because of the way we have to, multiply or modify these things together. A lot of this, you generally won't have to do a lot of this reshaping of stuff. Maybe a couple places in some other models we'll look at. This is just because I'm using just a hard-coded equation, I guess you could say. A lot of them are, most of the examples we'll look at are really designed for image classification, so we don't have to do a lot of this convoluted stuff. And again, here's our simple training loop. You can see we're going through the range of the number of epochs. We're doing a Y prediction, calling our network. So our network here is this, right? And we just call the network itself using the X train, which is those data values. So the X train would be those 8 values here. So 8 values of these. And then our predicted values is what's calculating, right? So when we pass these through our network, what the prediction comes out is what it sort of thinks it should be. So what the output should be. And ideally, we want it to match the function this function here that we originally looked at, okay? And we can run it, and this is it running through, and you can see here, after a short period of time, after almost 1,000 epochs, it derives at a loss of almost 0. And then for the rest, we're also doing validation or test loss in this case as well, just to determine how accurate we are. And you can see that's almost going down to 0, but then it sort of wobbles at the bottom. Okay, and you can see here's our plot for the history, and it sort of finds its way down to there. So, and here's the final example where we're just taking 25 random values for X between the range, and we're plugging that back into the network, doing the predictions, and this is what comes out as the output. So we're essentially seeing how well our function approximated to. And you can see there's a couple bad values here. The clumping up is probably a result of just bad randomization, I guess. But you can see that, the gaps aside, some of it's good, some of it's not as good as we might expect, right? We're getting a loss of 0. We should expect this to be almost perfect. So, but let me just demonstrate a couple things here. So what I'm going to do is I'm just going to change the learning rate to 0.36 and just see what effect that has. And if you're following along, feel free to do that. So what I'm just going to do is run time, run all. That's just going to run everything in this sheet. It'll run it pretty quickly. You can see there it's training, and you can see my loss is going down, but it's not actually becoming 0. And you can see down here, it actually jumps up again, right? Around 4,400 epochs, it jumps up again, and then it decreases again. And we can see that here where we get that jump in the loss. And if I actually increase that a little more, say to 0.5, so you can see here at a learning rate of 0.5 or 0.05, 0.05, which is about 5% of the loss getting pushed back, you can see my network is never going to get under 1,000, right? And our resulting plot is going to be totally bad. And that's almost just a difference of doubling our learning rate did that, okay? So that's what we're sort of going to talk about now, is how much learning rate and how the data we're looking at can really affect how a network learns. And this is a really good example of that. Okay, so let me just jump back to the slideshow. Is there any questions on this stuff? No? Okay. Okay, so that really exposes the sensitivity to the learning rate. You can see it's almost like, in some cases, some people might call it as like an inflection point where you'll have the learning rate doing not very well. You know, it might initially train very well because the learning rate's applying a good amount of change to your weights, but then it never sort of finds that real value because it sort of bounces around. And that's where, you know, if we look back at the DC GAN example, where we have a lot of bounce in our gradient or loss, that usually means our learning rate's a little too high. We don't want to get a lot of bounce. We often want to reduce that bounce or the amount of, you know, change in our graph as much as possible. And doing that, we usually do that to because it's just essentially a lot of wasted effort. This bouncing around is a lot of wasted effort. So by reducing the learning rate, we're essentially making our network more efficient, and it should train ultimately sooner, but it might take more epochs, I guess you could say. So it's kind of one of those things you have to play with. It's one of those parameters you have to, or hyperparameters you have to look at. So here's a previous example of what I had ran using, I think it was 0.26 learning rate. And a lot of these results are going to be dependent on the randomness of the test selection, essentially. And I just relied on the randomness of that to sort of give you this. But, you know, you can see some differentiation. I think this example here was with that 0.25 learning rate. And you can still see it's not optimum. It comes to a point where it's getting to 1,000, then all of a sudden it actually finds that low spot and is able to minimize the loss to 0, but that's not always guaranteed. Okay, and here's the attached graph, which again is so-so. Okay, and this is a part that really frustrates a lot of newcomers, is because you know, they're looking at these examples and it's just a simple thing like learning rate. That's why is it changing this is so much, you know, causing me to lose results, or it's taking so long to train and I'm not really seeing good results. And this is one of the things where you have to sort of balance that learning rate with all these other things we'll look at here in a short bit. Okay, so in order to understand this, let's sort of take a look at and review what calculus, because we're using calculus in deep learning networks to do the backpropagation, right? Remember, backpropagation takes place by calculating the gradients of all the weights in the model, and we do that using calculus. So in order to do that, the function that we're looking to approximate, or the function that we're going to approximate, always has to be continuous. So if there's any breaks in the data or there's hard edges on the data, that makes it a lot more difficult for our deep learning models to sort of adjust and find the solutions. This is why you'll often have people that are trying to use tabular data on models that might have discontinuities in that data. They'll have problems training deep learning models. And the reason is because it's just a deficit of the deep learning networks. They just can't do discontinuities in data. And that's just something to be aware of overall. But so because we're looking at, and we're always looking at continuous functions, and we look at sort of the objective function we might be trying to fit, saying this is maybe an example of a function we're trying to map across. You can see here that, say I have a gradient that's pushing this way, and my learning rate is large, right? So I have a largest learning rate, and I'm trying to apply it to the gradient to determine the loss so I can map against this function, right? But you can see here, if the gradient's quite large, I'm going to overshoot and likely undershoot spots on my function that I'm trying to approximate, right? So the way we can resolve that, and the way I showed you how we can resolve that, is just by reducing the learning rate, is a simple way. The other ways we can do, not by just introducing lower learning rates, but more data, because more data gives us more, just got to let somebody in. More data gives us more areas to sort of follow along that plot. if you look back at our original plot or function plot, we only had like 10 points of data. So the gaps between our data were quite large, and that those gaps are essentially called the latent space. Those latent space gaps are quite large, and sort of define those, to approximate across those gaps can be problematic, especially when the model's multi-dimensional, right? Okay. Okay, so let's look at this this learning rate example quickly that shows you how we can sort of make that learning rate a little more gradual. So let me just stop sharing and I'll share. Okay. So this example here is Gen 3 learning rate. This should be on the repo as well. This is basically pretty much the same example. The only difference here is we're adjusting the learning rate and we're reducing the number of epochs. So notice here that I'm reduced the number of epochs from 8,000 to 2,000 because I know that by reducing the learning rate, I can come to a more effective and optimal solution, okay? You can see that I'm reducing the learning rate by 1/10 of what I showed you last time. So we're 0.005. And now let me run all this again. Okay, so you can see our loss here follows a nice slow trajectory down, and our test loss even goes not too bad. I mean, we could probably train a little more to get the test loss reduced, but for this graph, this is a really nice graph. And by the time we reach zero loss here, we know that the model's trained. So somewhere around this point of 1,500 epochs, we could probably cut this off and be happy with this, I suppose. That would probably be around here. So maybe a loss of 6. So I guess the 2,000 is good for this example. And then you can see this is our fitting of the data. You can see there's probably just still a little blip down here. And that might be because in this example, keep in mind that we're only using 10 points of data. So by cutting out 20% of our data, we're essentially, creating huge latent spaces in our data. So we could expect to see some problems. And that's where a lot of people ask me, well, how much data do I need when I'm training deep learning networks? And it really depends on the size of the network you're trying to train. That's really critical. If you're training a really large network, you want to use a lot of data. And the reason why you want to use a lot of data is because you can fill in all those latent spaces in the network. The other way you can sort of reduce that problem of getting these sort of missing pieces, or what we might call overfitting, is to reduce the network size. So we could always come back here, for instance, and change this network size to maybe half that. So we could reduce this to 25s, for instance. Okay. Let me just reduce these to 25 because it likely doesn't need to be 50s. It might be, I mean, with 2 layers, it's probably overkill as it is. So let's just see. So I've just essentially quartered the size of the network, and let's see what results. So you can still see the loss graph is going down quite effectively, but you can see the loss is not what we got before. So this would tell me right away that 50 actually makes sense to train this model quickly enough. I could probably up the epochs here to 3,000 and see what the results are. But this is just one of these things where we play with, the hyperparameter tuning to sort of optimize our models to determine how big or small. Now, model size can be important later on when we're training models because, as Dave mentioned, he was running out of CUDA memory. And how you can run out of CUDA memory is you just have so many parameters in your model. The model gets so big that you just run out of GPU memory, essentially. And I think on a collab, it's 15 gigabytes. So it's not a small amount of memory. We'll be building some pretty big models with lots, millions of parameters, essentially. So here you can see, I just increased it to 3,000 epochs, and I'm getting it almost to 0. Still getting a quite high test loss, but otherwise. And for this example, the test loss is not really, it's not really a critical factor because it really is only 2 points in this example. So it's not really And you can see here, we're getting a couple spots, again, that are fitting maybe not quite well. And that's probably because of the test. If we increase this to more data points, for instance, we'd probably get a better fitting graph. And that's because we're reducing that latent space. And that latent space is this area here, right? And we'll cover that again. So let me just go back. Any questions about that stuff?
Hey, Michael, I have a question if you don't mind.
Go ahead.
So I guess one of the things when it comes to data is a bit of a data augmentation, right? That you cannot read to enhance your input data. What role does it play when you don't know kind of like the shape? Because here the model what should be adjusted to is the x squared plus 5. When you are not sure, how can you augment your data to improve the result?
Yeah. So in the DC GAN example here, I think. No, I don't have that. But one of the things we could do is there's, for instance, in this just simple example, I can go transforms, random, I don't have, but it's random horizontal flip, for instance. So we can actually use a transform to do a random horizontal flip on the data so that our faces are actually randomly horizontally flipped. And that can be a way to augment the data. Other ways to augment the data is maybe to flip it. I mean, if the image orientation isn't important, we can do flipping, or we can do masking in certain parts of the image, for instance, to augment the data. There's lots, for image analysis, there's lots of ways to sort of do that. And there's a lot of helpers here to do that sort of thing. There's transform, random horizontal flip, vertical flip. There's sort of random croppings, for instance. There's a lot of various transforms that can provide that sort of data augmentation for you out of the box, essentially. Does that help?
Thanks. That's pretty tricky. Thanks.
Okay. Okay, so let me just go back. Okay, so really what we're talking about in a lot of cases is managing over and underfitting, right? And a lot of times, if our network is too small, or we don't have enough data, or the learning rate's not fine enough to pick out the model, you'll typically run into underfitting problems. On the opposite side, if you have not enough data, or the network's too big, or generally not the learning rate. The learning rate might still be small, but for instance, if you have a network that's really large, is the learning rate dependent on the sigmoid function than using other activation? No, the learning rate's really dependent on the data that you're sort of mapping across and the size of your network. So smaller networks should probably be able to get away with larger learning rate values, where larger networks with a lot more hyperparameters, you often want to reduce your learning rate because you're training a lot of hyperparameters and you don't necessarily want to influence any one of those values. And there's a lot of other tricks we'll look at on how to balance that. We'll get into as we go through, but this is just, wanted to keep it fairly basic right now. Or you can get into this sort of the problem of overfitting. And a lot of people don't realize that if you make your network really, really big, so if you put a lot of parameters in your model, a lot of nodes or stuff like that, you'll probably get good results. But the problem is you can actually get the network memorizing data. So this is a good example here. If I go back to my last example, where you see the loss going down to 0 on my training data, but on my test or validation data, it was going up. It was actually going up to 117 or 120. And that would be an example of my network overfitting to the data. It was becoming too specific to our particular example. Now, in that particular case, it was just a poor reflection on how much training or validation data was used. But that's an example of overfitting, where you're getting that discrepancy between your training and your test or validation data sets. And what you want to do is you always want to make sure those things are converging. Okay. So here's an example of, I think we have enough time to cover this, over and under fitting. So let's look at that. I wish I could just share my screen. Okay. Okay, so this is the over-under-fitting example here. And so what, in this example, instead of doing a set of points, we're actually doing this NumPy arrange, which essentially allows us to take a range of data and set the step size to generate a number of points, okay? And in this case, I think it's generating, well, the step size is 0.1, so it's 100 points. So we'll actually see 100 points of data through here. And you can see this is getting plotted in red. We're doing the same thing where we're taking the train test split. We're using a test size of 20%. And now I've set the neurons here so I can be able to change the neurons on the fly and adjust this to see how it might affect the model. For right now, I'm setting it at 20, and I'm setting the number of epochs at 1,000. So pretty much exactly the same solution. So let's see what it looks like. So let me just run all again. Okay, so what you can see here is with this 20 epochs, or this 20 neurons, sorry, my test loss is almost the same as my training loss. And that's typically what we want to see. And the reason why we're getting that in both is because we're using a lot more data points, right? We're not using just a small amount of data. We have a lot of ways to fill in those gaps. So we're getting some good consistency. You know, out of those 100 points, we actually have 80 points are going to training, 20 points are going to test. You can see when we plot the history, we're getting a nice smooth graph here. And when we plot this, you can see that we're getting a relatively nice smooth function. We're getting a little bit of problems at the top here. I'll talk about that a little later. But what I could do though, is I can quickly change this to 50 again, and let's run it all again. So this is going to change this to 50 neurons throughout our model, just like it was originally. And it's done. And now you can see here, my loss is 3 and my test loss is 8. So who can tell me if that's over or under fitting? Does anybody know? Anybody want to shout out the answer? Nobody's ready for questions. Oh, we have somebody. Okay, go ahead. Overfitting.
Yeah.
Yeah, exactly. So what we're seeing here is the model is overfitting to the data, and it's not going to effectively do. So if we're to throw this model out into the wild and try and use it on real data now, our loss would be probably more unpredictable. And what we really want to do is to maintain that these are both the same. So let's go back here. And what happens to reduce this down to 15 or 10? Let's say 10. And our loss isn't really going down. You can see the numbers are reasonably good. You can see that this loss, though, is larger than this loss for some reason. You can see our graph is doing little funny things. It's flattened out here. What we're seeing here is an example of underfitting, okay? Because as much as we have enough data points and stuff like that, our network isn't big enough to map all the data, right? So this is a case where our network just isn't big enough to learn the example. Now we can rectify this a couple ways. Like I could, for instance, try and increase the number of epochs, say to 3,000, and run this again. And not too bad. It's a little closer, but you see there's still, almost 3 times difference here. And let's see what our graph looks like. Still not too bad, but you can see this bottom piece looks like it's still flattening out. Still not the best. So I would say this model, probably the 10 neurons isn't really big enough. No matter what we do, we sort of need more neurons to be able to fit this equation. As much as this equation seems really simple, we need more neurons. The other thing to note is I sort of took out one layer there as well. If we probably add in another layer, that would probably make a difference. Like if I just quickly add in another layer here. Okay, so let's just try run this, see what the extra layer does. Oh. Oh, whoops. Can't do that. Okay. So what happened there? Because this is our input, but this has to match this. This can be whatever, but this has to match this. And likewise, this has to match this, right? So those numbers all have to be the same. So let me just run it again. Okay. So by adding the other layer, you can still see we're getting almost a 3 times loss, and it's still doing the same thing. So even adding another layer didn't really matter that much. Really, to balance this out, I'd probably have to increase that to 20 neurons. Let's just run it again. Okay, so not too bad. This is getting down there. It's still quite an increase, but let's see what our graph looks like. And that graph isn't too bad. So you can see this is an example where you can play with and understand a little bit of over and under fitting, how you can adjust those parameters in the model, and see what effect that has. So that it sort of gives an idea of how much data you might need for a model, is to do this sort of exercise like this with the data you're using. So if you pass it through the model and you notice that your model isn't fitting well, you're getting your training loss is substantially different than your test loss, then you need to adjust your network, or you may need more data or other things. So that's one of the things we're looking at. Any questions, guys? No? Okay. Oh, I'm going to share my screen. Okay. So really, so the things we want to look at when we're trying to resolve over or under fitting problems is, is it trained enough for enough repetitions? And this is the first thing you'll often look at, but it's something you might revisit. You want to look at the learning rate. You want to look at the network size. You want to see, is the network big enough or small or too small for your problem? And that's where you can sort of look at that training and testing loss to see how well they're converging. Okay, and is your analyzed data distributed well enough? And we're going to get into that in a second. So in what situations does adding layers improve fitting? Well, so in convolutional layers, when we're doing image extraction stuff, we'll often add a number of layers of convolution. We actually might add several layers of convolution. Like there's models with hundreds of layers of convolution, for instance. So in this example, we might have 3 layers of convolution doing extractions of features, and 1 layer here, just a typical sequential or fully connected layer at the end that's sort of giving our answer. So that's typically where you'll see these types of things. And that's the type of models we'll get into, especially when we look at residual networks where, you could have a 100-layer model, for instance, where we might look at something like that. But that's really more for extracting features and understanding what those features do, that we can either sort of use those for classification purposes, or as we'll look at later, for generating new images or new features. Okay. So ultimately, really, our goal is to minimize or make uniform the latent space. And so when I looked at, when we looked at earlier, the latent space is that distance between our data points. If we were to look at or think about it as the MNIST data digits, which this example here is just sort of a latent space modeling of the digits across a learned model. And the other image here is essentially a cosine similarity or cosine distance passed across those data. And this is probably through, I think this is probably through a variational autoencoder, which we're going to look at here in a minute. But by understanding that latent space of the encoding in an encoder, we can then use that to map where the images are, or even understand how differences between the various latent spaces between classifications or classes in our data, for instance. We'll get into that. Okay. So again, so what is the latent space? It's that distance between our data points, or what our model is trying to fit across, right? And keep in mind, this is a simple 1D problem we're looking at. I know it's a 2D image, but think about it. It's really all we're doing is sort of looking at, predicting from the value X. So our input is one dimensional, and we're looking for an output of one value, as opposed to, when we look at more complex problems, we're looking at classification of MNIST data. It's 28 pixels by 28 pixels. That's 784 dimensions going into our network that we might reduce or we might increase. We might increase it to 1024. That becomes really complicated functions that we're sort of trying to map across. And that's why we have to think about the amount of data we're using. Okay, so let's look at an example here. We're going to jump up to an example of variational autoencoder. Autoencoders are a great way to sort of understand this stuff, and the variational version here is a great way to understand how we can look at understanding the latent space, not just in sort of distances in a function, but distances in the distribution of data. Okay, so let's just take a look at the example here. Okay, so this is it's actually a convolutional variational autoencoder. The only difference besides what we consider maybe a vanilla or a standard variational autoencoder is we've added convolution. And the reason we've added convolution is just to sort of see better results, essentially. In this example, we are using, I've set the runtime on here to be GPU, so it should be set to GPU by default. And this line of code here just extracts which type of device we're using. So again, if we're using a GPU device, it's going to come back as CUDA. Otherwise, it's going to come back as CPU. And the difference here that it makes is that for all our deep learning activity that we do for anything in the model, we have to convert those to GPU tensors so we can do the computations on them. And I'll show you examples of where we have to do that here down below. Okay, so here's our transforms. In this case, it's pretty simple. We're just doing a transform, resizing the images to 64 pixels by 64 pixels. And that just gives us a little more space or a little more data. It may not be intuitive all the time of why we might want to resize images to be larger. The CFAR 10 data set that we're going to be looking at is actually only 28 by 28 pixel, 28, or is it 32? I think it's 28 pixel by 28 pixel. But the reason why we're increasing it up to 64 is because for every layer of convolution, when we apply that convolution by applying the filter, we always sort of reduce the image size by a pixel or two. And that's just a result of convolution. So in order to apply more layers of convolution, we have to actually increase the image size to a substantial size. So a lot of those models that I talked about earlier that might use 100 layers of convolution might also expand the image to up to 1024 to 1024 or 224 by 224 pixels, okay? No, irregardless of what the image size is, they'll just sort of maybe adjust that size based on how many layers that need to be passed through the convolution. And that just allows us sort of to extract all those features as it goes down. So every layer of convolution will essentially crop the image a little bit as it goes through, okay? So here's our batch size. Here's our typical hyperparameters, batch size, epochs, and learning rate. You can see the learning rate here is set to 0.0001. And here's our training loader and testing loader. Again, these are just really a simple example. This piece here is just for rendering the image itself so we can look at the results. And this is just a function to render the images. And here's the classes in our data set. So this CFAR 10 is, I think it's 160,000 images. I think it's somewhere around 60,000 images or 70,000 images of these 10 classes. So there'll be a whole bunch of different variations within each of these classes. And here's an example of that again. So you can see there's a horse, dog, etc. Planes. And planes can be everything from this biplane to jets and stuff like that. So there's a lot of variation. I mean, it's not a really easy training data set to teach a model on, but it's one of the sort of basic ones we'll look at. This flatten and unflatten function, this is just for sort of taking the model from that 64 by 64 pixel image and flattening it down so it can be used in sort of regular linear layers, okay? So here's our convolutional variational autoencoder. And this is an autoencoder. So what we have here is essentially like a GAN, but it's reversed, right? So we have the encoder, which works kind of like the discriminator, where it's encoding the data down. In a typical autoencoder, the encoder encodes the data down to some latent space or latent sort of representation of the data. And that latent representation might be a vector of 2 or 32 values, for instance. In this case, though, in a variational autoencoder, we're actually reducing this down to parameters called parameters for the distribution. So what we're trying to learn in a variational autoencoder is how the data is distributed in the image. And then by using those understanding of that distributions of the data in the image, rebuilding that using the decoder, okay? And I have a diagram that sort of explains this in a little more detail, but I just want to look at the code. This reparameterization is essentially just taking the learned parameters from the distribution. So in this case, the mean, mu, or standard deviation, and the log variance or the standard deviation, okay? And we'll get at that. And then these other functions are just some basic things. I'm not going to spend too much time on that because we're running out of time here pretty quickly. So here's our optimizer. And the loss function we're using in this case is binary cross entropy. And we're using a sort of this function here is sort of a method much like Kullback, Lieber, or Jensen-Sanin for measuring differences in probability distribution, differences in the distributions, okay? And I have another plot we'll look at, but so that's the basic of that. We'll get back to this in a second just to see how that plays out. And then here's the typical training loop again. So here we're pulling out the images. And so what I'm doing here and what I'm doing up here, let me just go up here. So when I'm calling the model, you can see here I'm calling the model and I'm saying to device. That essentially means I'm creating the model to the device, and the device, if you remember before, up farther, one of our first lines of code here is define it based on if the notebook is using a GPU or a CPU. So this, we're essentially setting the tensors of the model in this particular line of code. This sets it to either CPU or GPU, okay? And that gives us the ability to calculate either with a GPU or CPU. And using GPU will generally be about 100 times faster, depending. I'm using Pro, so I think it gives you a little bit better, better GPUs on average. And I think actually if you don't have Pro, they can actually not provide you with GPUs sometimes if it gets too busy. But most of the time I only have Pro when I'm writing. Most of the time, it's not a problem. It's not something you really have to typically worry about. So I'm not promoting Pro. I'm just saying it's a nice to have feature, especially for me for $10 a month. Okay. So and here's so this is where, for instance, we zero the optimizer, and then when I'm turning the images. Whoops. So the images come in as a tensor, and the tensor is just a normal tensor, and what we have to do is convert that tensor to the type of device. Now, if this is a CPU, it essentially wouldn't do anything, but because it's a GPU, it's actually converting the tensors to GPU tensors. And then those get passed to the model. And what we're getting is the generated, so essentially the generated images and the distributional parameters. So the mean and essentially standard deviation. And then using our loss function, we can determine our binary cross entropy loss and this sort of distributional parameter loss. Those things all get sort of totaled up, and that becomes a training loss, and then that training loss is something we push backward, essentially. That's that loss here that's getting pushed back, okay? And then after about 100 iterations, this is, you can see this is what we're getting as the results. Now, the results aren't bad. I mean, you can kind of see a deer. This doesn't look anything like an airplane, but I suppose that looks like an automobile. And a lot of that is because really the domain of our data is really inconsistent. We have a lot of variations in the data. It's really difficult to learn. And that's one of the tricks for using faces, for instance, because faces will really give us a good uniform data set. It doesn't give us a lot of variation in that data. And you can think of the variation of the data as sort of the gaps in the latent space that we have to fill. So if you're trying to match a truck in one image to a dog in another image, you can think that there's going to be large amounts of gaps between those two that you have to map across. And that's kind of some of the problems we're having with this model, even though, you know, in some cases it's not doing too bad. But those are some of the problems we have to sort of account for as we go through the other sessions. Any questions about this example, guys? And if I'm going too fast, please tell me. You can always slow down and adjust the way things are going. Okay, so here's how basically how a variational autoencoder works. We look through the code. And hopefully this will make a lot more sense. So X is the encoder piece here, and this is encoding down. So what our model does is it sort of takes the image and it encodes it down into this final output. And the output is actually, what it outputs is the mean and standard deviation. These are the learned sort of parameters that are being taken from the model. So instead of reducing this down to, in a typical autoencoder, we might reduce this down to a vector, you know, maybe a 5 or 10 or 30 dimensional vector that represents the encoding. We're actually just reducing this to 2 parameters that define the distribution. In this case, it's just a normal distribution, but it gives you some idea of how we're defining that. From that distribution, then we use the reparameterization and sampling function to sample from that. And based on that sampled data, we rebuild or reconstruct the image with the decoder. Okay, so remember, in a typical autoencoder, all we're doing is reducing this down to a latent space or latent sort of representation of the data, and then we're rebuilding that. In the variational autoencoder, we're actually learning some distributional parameters about the data itself. So it makes it a little easier for us to rebuild that data or understand what are differences between the loss of that data. Okay.
Michael?
Yes.
So just in that, and for each sample going through, then is it's reporting a mean and standard deviation for the sample, or for a batch of samples, or for the data set as a whole?
Yeah. So keep in mind, because the batch we're throwing to is 32 images, it's going to give us essentially the mean and standard deviation for each of those images, right? But it's calculating them all in the batch. And the other thing to remember is it's not calculating that, it's actually learning how to calculate the mean and the standard deviation of the image. So what the normal distribution is, okay? So you can think of it as the image that's trying to be generated might look like this distribution of data, where the image that it's actually trying to generate is this distribution. What we're trying to do is match those distributions, right? And so we're using Kullback-Leibler or Jensen-Sanon or binary cross entropy as a means to measure that difference in loss between those 2 distributions of data, okay? So you can think of it as if, you know, in a discrete value, a smile we might register as sort of, you know, negative 0.8 or something like that, to a value of 0, to a value of maybe 0.5, to a value of 0.75. But what would give us more information is actually understanding what the distribution of that smile is. And that's what we're looking at, and what sort of makes a lot of important sense when we look at generative modeling, essentially, is really understanding how that data is distributed and how it fits that distribution. Okay. But keep in mind that in that standard variational autoencoder, we just assumed a normal distribution. But keep in mind, data distributions can come in many different flavors, right? A lot of times we'll use a normal distribution, but distributions can come of anything, right? And as we get more advanced, we can even look at different ways of randomizing our data. You know, you might not just use a uniform distribution, what we typically use. We might use some other different distribution, right? Okay. But here's another way to look at it as well. So you can think of it as the generated distribution might come out as something like this, but the actual true data distribution might be something like this. So the loss is the difference between those two distributions. And what we're trying to do is minimize that loss, right? So that's really what we're trying to do. In the variational autoencoder, we're trying to minimize that loss. But really in generative modeling, it really comes down to understanding the distribution of our generated data and the distribution of our true data and how much those differ. So that's really the key of what we're looking at, okay? I have another example here, the variational autoencoder that shows the latent space. I'm not going to go through that. I'll encourage you to go through that. But essentially what all it does is it just shows you using the learned distribution parameters, we can turn those back into the model, and we can actually start to generate what that latent space looks like. So we can fill in values. We can arbitrarily pick those values and fill those values in, and that'll give us an understanding of the latent space. Now here's an example. This is probably a generator that's using a different method, and it gives you an example of what that latent space might look like if we're moving across the distribution. You can see here we have a man with a beard, and as we move across that distribution, his head might be turned, or there might be other discrepancies. And that's the way to think about variations across the latent space and how our models learn, right? And the more variations across and the more gaps we have across that latent space, it's harder for our models to generate data, but not only learn how to generate that data, but generate the data itself. Okay, and here's some really good examples. So I think this is with a adversarial latent autoencoder, which is sort of kind of the same makeup. We'll probably look at that much later in the meetup series. But here's an example where you have gender, age, hairline, and stuff like that. These are sort of learned conditions that we can then map across. You can see all these different changes as you apply them to the different model, right? And some of them are taking effect and some of them aren't taking effect. And we'll look at examples of that as well, of doing conditioning across distributions. So any questions, guys? Any questions or things you want me to go back to or look at? No? Was this too advanced or not advanced enough? And you guys just want to answer yes or no in the chat window, please, for me. Too advanced or not advanced enough? Okay. Okay, so it's about 50-50. So if it was too advanced, where did you get, at what point did you get lost? So if you found this too advanced, what point do you think you got lost? The encoders? Yeah, okay. Yeah, we covered encoders already, and I didn't really want to go over that too much again, but that's something I typically do for an intro to deep learning session. Okay. So next time we'll probably be looking at a lot of different variations of GANs and stuff like that. Now, so if we go back to a lot of GANs, will use that understanding of distribution to determine the loss, and that's why I sort of introduces the variational autoencoder and talking about the latent space. And as I mentioned, this is probably a little dry, this discussion, but Okay. Great, everybody. Any other questions, comments, thoughts? What could we do better? Okay. Okay. Great job, everyone. Thank you. The PowerPoint. Yeah, I'll probably I could put the PowerPoint up on the repo probably. I'll do that. Okay. Thanks, everyone. Have a great night.
Thank you. Same.
Thanks.